in the interest of time, I think we'll switch, but we'll have a break right after the next talk. So hopefully we can catch up on discussions. So the last talk of this morning, first half of a session, I should say, is again by our very own Blake Richards. It's a morning session of Montreal brewed science, which is quite nice. So Blake is a professor at McGill University, jointly appointed between the computer science and the neuroscience, or at the neuro, right?
Yeah,
What's
the neuro,
okay.
that works. Yeah.
And also a core academic member at Mila. And today Blake's going to talk to us about brain-like learning with exponentiated gradients. So please take it away.
Thanks, Guillaume. It's lovely to be here with you all. Always a pleasure to be at Maine. Thanks to the organizers for having me. Thanks to the real organizers for having me. I was tempted to do a talk on foundation models for neuroscience, but a lot of what I would have said about that would be repeated by a later speaker in the day, Eva Dyer, so I'll let her handle that on my behalf. She has lots to tell you about that, and we'll discuss it during the panel as well. I think it's a fascinating area. But instead, I'm going to tell you about something that my lab's been studying in the last couple of years, led by a postdoc named Jonathan Cornford, who is now off to his own faculty position at the University of Leeds. And I think it's an important story because I hope it will be something that will be adopted by the computational neuroscience community at large, or rather the neuro-AI community, as it were, i.e. people who use artificial neural networks to study the brain. So let me just jump right into it. All right, let's begin with the question of what it is we hope to actually achieve in computational neuroscience with our models. I think this is often not made explicit enough. I think sometimes there is a naivety about what we're doing and some idea that we're seeking a model of everything. But of course, modeling doesn't work that way, and no model is actually true. There's that famous adage, all models are wrong, but some models are useful. So what makes models useful? Well, it depends on what your goal is. There are ultimately different ways to model the brain, and there are different things that you should be concerned about when you're modeling the brain, depending on your goals. So if you're really interested in the biophysical mechanisms of the brain, then you should build biophysical models and, do full-scale integration, numerical integration of all of the different compartments in a gigantic neuron model, and that can tell you a lot about the biophysics potentially. Alternatively, perhaps you're more concerned with a model that matches the phenomenological experimental data that we see. So whether that be plasticity curves like spike time independent plasticity, or the particular distribution of synaptic weights that you see in the brain, getting something that can link explicitly to the sorts of phenomenon that we can observe experimentally might be your goal. Alternatively, you might be interested in normative models, that is, models that have been optimized to actually perform some task, some behavior. And ideally, it would be a non-toy task of the sort that animals can actually perform. Now, of course, it should be said that the ultimate ideal is a multi-level model that links one or more of these other model types. And so our goal in computational neuroscience is ultimately to try to move more and more towards models that can stretch across these different levels. And so what I'm going to tell you about today is a learning algorithm that we've been studying in my lab, which I think does a better job of stretching across these models than the current standard learning algorithm used for training artificial neural networks in computational neuroscience, which is gradient descent. So, indeed, gradient descent is the go-to algorithm for normative models in computational neuroscience. The reason for that is very simple. Gradient descent works. I spent my early years as a graduate student, whenever I would delve into computational neuroscience papers, for the most part, what you'd find were models that would perform extremely toy tasks, like basically associate A with B or something like that. it was really only once people started adopting gradient descent, i.e. backpropagation at large, that we started to develop models that could do things like recognize images, solve multiple different tasks, process speech, control a robotic arm, etc. So the principles of gradient descent I won't belabor, but I'll just review it very quickly here. The core idea is that if you imagine your space of potential synaptic weights, illustrated here with two synapses, so synapse 1 and synapse 2, and then you quantify how well you're doing at your task with a loss function, where the higher the loss function is, the worse things are, the lower it is, the better it is. Then ultimately we can view learning as being the goal of trying to find the point in this synaptic space that minimizes this loss function. And so gradient descent as an algorithm gives you a very simple solution for this. It says, well, wherever you are currently in your loss space, WT, this is the current synaptic weights at time t, so that would be a vector of synaptic weights with time indicated here. What we're going to do is the next set of synaptic weights at time t plus 1 is simply going to be the current weights minus the gradient of the loss function with respect to those weights times some learning rate to make it a small step. So if we were located here on the loss function, we're just going to go down the hill, basically. Just walk down that hill. It's an incredibly effective algorithm. It has underpinned basically the entire revolution in AI that we've seen over the last decade, and as a result, it gets used constantly in computational neuroscience for very good reason. Indeed, I couldn't help but do this search because I was curious to see, you know, like I said, when I was a graduate student, people did really simple models, associate A to B. It was all Hebbian learning. And so I'm pretty sure that if I had done this Google search comparison 20 years ago, Hebbian learning would have come out way on top in terms of the number of citations for Hebbian learning neuroscience. But nowadays, gradient descent neuroscience is winning this game. And it really goes to show how ubiquitous gradient descent has become as a tool within computational neuroscience. Now, the problem is that gradient descent violates a series of physiological and phenomenological properties of the brain. So if we want a multi-level model, it's not ideal. It's great for a normative model because gradient descent lets you train a network to accomplish some behavior very effectively, but it's not so great as a multi-level model. There are a variety of things I could talk about, but today I'm going to focus on two properties in particular of gradient descent that are problematic from the perspective of trying to actually model the brain. The first is that it violates a basic tenet of physiology, which is Dale's law. So Dale's law states that neurons release the same set of neurotransmitters at all of their synapses. To be clear, as with all things in biology, Dale's law isn't actually a law. There are a few neurons in the brain that violate this. But it's about as close to a law as you can get, and certainly within cortical systems, this is roughly true. But what Dale's law means practically from the perspective of modeling the brain with a neural network is that you cannot have cells that switch from being an inhibitory cell to be an excitatory cell, or vice versa. That's because, according to Dale's law, if I'm a neuron that releases GABA from my axonal terminals, A, I'm going to release GABA from all my terminals, and B, I can't release any other neurotransmitter. And since the action of GABA at the postsynaptic receptor is generally going to be inhibitory due to the fact that it opens chloride channels, you're going to be always having an inhibitory impact on your postsynaptic partners if you're a GABAergic neuron. In contrast, if you're a glutamatergic neuron, you're going to be generally activating ion channels that allow for the passage of sodium and potassium and calcium, and as a result, you're going to have an excitatory effect. So technically, neurons in the brain cannot change from being excitatory to inhibitory or vice versa. And yet that is exactly what gradient descent does. If you watch the dynamics of synaptic weights in a model trained with gradient descent, it's going to switch the signs of your synaptic weights ad nauseum. Now, it also violates a phenomenological observation that people have made. So when people examine experimentally the distribution of synaptic weights in the brain, so here, this is an illustration from a review. So let's say you do a very simple experiment. Well, no, sorry. The experiment's not simple. It's conceptually simple, but not technically easy to do. But let's say you do this conceptually simple experiment. You patch multiple cells, and you look at the postsynaptic potential that's created in the postsynaptic cell when you activate a spike in the presynaptic cell, as illustrated here. And then you plot out the strength of that postsynaptic potential across all of your neurons. What people have observed is that generally these measurements, which are basically a measurement of your synaptic weight, because you're looking at how much of an impact does the presynaptic neuron have on the postsynaptic neuron. If you look at this distribution of what is effectively your synaptic weights in the network, it tends to be log normal. So if you look here, this is a logarithmic axis. So this Gaussian shape is ultimately indicative of a log normal distribution. But gradient descent does not produce log normal weight distributions. If you train a neural network with gradient descent, you get generally Gaussian distributions in your synaptic weights. So none of this subtracts from gradient descent's power as a normative learning algorithm, but it does mean that if we're trying to inch towards better multi-level models of the brain, it's perhaps not ideal. So can we develop something that doesn't violate these principles? Can we get to the point where we not only have this normative component for gradient descent that it gives us, but something that ideally doesn't violate something as basic biophysically as Dale's law and doesn't lead to a clear split with the phenomenological data with regards to the synaptic weight distributions. Okay, so is there an alternative algorithm that will be better as a multi-level model of the brain? So let's start with a normative question, because here's the thing. Above all, we don't want to sacrifice that normative power. With all due respect to every one of my colleagues in computational neuroscience, this has been the mistake that we all, myself included, have made in various studies. When we try to develop alternative learning algorithms to model the brain, often what we do is we develop algorithms that just kind of suck relative to gradient descent. So, you know, we'll be like, oh, look, it's biologically plausible. Oh, look at all these ways it fits the data, etc. But like, if you try to get it to do anything other than learn like A is associated with B, it shits the bed. So we don't want to do that. We want to have an algorithm that's actually effective at learning complicated tasks. And the way you're going to get there is by ultimately deriving your algorithm from principles of optimization. So here's the core principle. What we want to do is we want to say the new set of synaptic weights that we have are going to get W at t plus 1. So WT, again, remember, is a vector of our synaptic weights at the current time. And what we want is for the next set of synaptic weights, W at t plus 1, to minimize this function. So what it's minimizing here is the loss function. That's the behavior we care about. That's why this is a normative learning algorithm. But as well, we want to minimize the amount of synaptic change that we actually have to make to the network. So this is a function, D, that's going to measure how much the new set of synaptic weights, W, are different from the current set of synaptic weights, WT. You can think of this as a measurement of the proximity in synaptic space between W and WT. How close together are they? So if you include proximity and then you derive the optimal learning algorithm, the algorithm you get will depend on the proximity penalty term you use. So here what I've done is I've redone that equation from the previous slide, but now I'm using a linear approximation to the loss. So this is just a first order Taylor expansion of the loss at WT. And here we have our proximity penalty term again. And we've just added in another little variable here, eta, which is going to end up being the learning rate. But you can think of it as basically a way of determining how much you're going to weight your proximity penalty in terms of determining your learning algorithm. Now, interestingly, if you set this proximity penalty term to be the Euclidean distance, so literally just the straight line between WT and W within Euclidean space, and then you minimize this function, so you get the W that minimizes this entire expression, what you get is gradient descent. So that's why gradient descent works so well, because it is literally the optimal learning algorithm to use when you have a Euclidean synaptic space. And this is why all of us have been incapable, I believe, of ever generating a learning algorithm that gets anywhere as close to as good as gradient descent when we're operating in Euclidean space, because literally it's the optimal learning algorithm. You cannot do better. So, but that only holds if you assume a Euclidean penalty term for your synaptic changes. What if you have a different term? So, for example, one term that you can use is the unnormalized Kullback-Leibler divergence. So that's this expression here. So this is the Kullback-Leibler divergence, and we're assuming it's unnormalized, so we do another little bit of manipulation of it here. So this is the ultimate expression. And if you use this distance function, which has some interesting properties, you get a different learning algorithm. You get something called exponentiated gradients. That's shown down at the bottom here. Exponentiated gradients says that the next synaptic weight at time t plus 1 is not the current synaptic weight minus the gradient, but rather it's the current synaptic weight times e to the negative gradient. So it's a different learning algorithm technically. Now it's still relying on the gradient, to be clear. That falls out of the optimization process, but it has different properties from gradient descent itself. Most notably, it respects Dale's law. So when you look at this distance function, this is why we started studying this synaptic proximity penalty term. When you look at this function d, you can think of it as a distance, but technically, mathematically speaking, it doesn't need to be. When you look at this equation here, note that you've got this term, the log of Wi, so the new potential synaptic weight, divided by the current synaptic weight, Wt. So what that means is, if I change the signs of the synaptic weight, if I go from positive to negative or vice versa, this term becomes undefined. In other words, the way that we've set up this proximity penalty, you cannot violate Dale's law. It literally says it is impossible for a synapse to switch from being inhibitory to excitatory or vice versa. And you can see that in the expression of the synaptic learning algorithm itself. So I don't know why I've lost my pointer now, but in the expression down there at Wt plus 1, as a function, there it is, as a function of Wt, oh no, it's not there. What you can see is that you can't switch the sign, because if Wt is negative and you multiply it with e to the negative gradient, you're not changing the sign, and vice versa. So necessarily you're respecting Dale's law. Okay, so the takeaway message is that gradient descent is widely used in computational neuroscience because it's very effective at training neural networks, but it violates known properties of physiology, i.e. Dale's law, and it also violates the phenomenological observations. So we've started exploring this alternative learning algorithm, exponentiated gradients, which, since it is constructed by a similar process of asking what is the optimal learning algorithm, but it's operating within a different set of constraints on the synapses, i.e. constraints that respect Dale's law by construction, then we believe that it should actually provide you with the same power for training neural networks as gradient descent, but in a manner that respects Dale's law, and we wonder, as you'll see in a moment, should also match the phenomenological observations better. And if so, it would be a better algorithm for using to train neural networks in computational neuroscience. Okay, so let's test it. So first of all, let's look at this weight distributions question. So what kind of weight distributions do we get? Is it the case, so as I've said, by construction, this algorithm respects Dale's law, but does it actually match the phenomenological data better? Well, in fact, if you think about it mathematically, it should match the data better. So one of the things that people have done within this space in machine learning when they've thought about these questions is the way that they've analyzed these learning algorithms is within a framework called mirror descent, where the way you can think about what's happening is that you have your synaptic weights currently, and when you're doing your update, what you're actually doing is you're transferring to a different space called the dual space. And that dual space is defined by the proximity penalty that you use in your algorithm selection process. And then you do an update in your dual space and you come back to your synaptic space using the function that brings you back there. Now in the case of the unnormalized callback-Liebler divergence that we were using as our distance metric, as our synaptic proximity penalty term, the way to transform a point in synaptic space into the dual space is actually by a logarithm. And then you're going to do an update in the dual space using gradient descent, and then you're going to transform it back via e to those parameters. What that means is that if you have a log normal distribution, you're going to transform it into a Gaussian distribution via this process. Then you're going to update it with a Gaussian update, and then you're going to put it back into a log normal distribution via the exponential. So this should produce log normal weights. To test this experimentally though, because like you can show it will in a very simple case, but let's look at what happens in a more interesting case where we're training a real neural network doing tasks. So in this case we used the ModCog suite of tasks. This is a group of 80 cognitive tasks modeled on classic neuroscience experiments where a recurrent neural network is tasked with having to take in 2 circular stimulus inputs, and then depending upon the rule input that it receives, when the fixation input drops, it needs to give an output to this other circular variable depending upon the rule that's specified. So for example, it could be something like output stimulus 1 after some delay, or output the opposite of stimulus 2 after some delay, etc. There are over 80 rules that are defined in this suite of tasks, and it's been used by a variety of people to explore the training of networks on multiple tasks, originally by Robert Yang. This is an expanded version of Robert's set of tasks. Laura's used this as well, many other people have. And it's a good set of tasks to explore for the purposes of comp neuro. Now, notably, exponentiated gradient and gradient descent can learn the ModCog tasks just as well as each other. So when we train a recurrent neural network on these tasks, using these 2 algorithms, the accuracy on these tasks shoots up at the same rate for the 2 algorithms. The final accuracy is identical. And even when you break it down across tasks, we don't see any difference in the algorithms in terms of which tasks it gets good at faster. So this is a measurement of the accuracy, and you can see that certain tasks are a bit harder for the networks. They take longer to get up in their accuracy, but that is basically matched across these 2 learning algorithms. But that doesn't mean that they're discovering identical solutions, because indeed, when you look at the synaptic weight distributions, exponentiated gradients gives you log normal synaptic weights. So here, I'm plotting on the x-axis, I should actually have that labeled, the strength of the synaptic weights across the recurrent neural network. And here I have the probability density, or the frequency with which we see those weights. And this is a logarithmic space on the x-axis here. So the result is that this is a log normal curve for EG, whereas for gradient descent, GD, it is not log normal. Okay, so it is true, EG respects the phenomenological data better than the, it started 5 minutes late, better than gradient descent. Now interestingly, as you saw from the expression, exponentiated gradient is a multiplicative algorithm. The new synaptic weights are ultimately a result of a multiplication with the current synaptic weights. So what you get then is a dependence on the new weights, on the old weights in an explicit manner, that rather the degree of weight change is dependent on the old weights. And this is actually what people see experimentally. So when you look at, for example here, changes in spine size recorded in the brain, the degree of change in a spine is actually a function of the existing size of the spine. So it's the same dependence on the current synaptic weights to determine how strong the new synaptic weight change is going to be. And that's exactly what you see with exponentiated gradients. This is the correlation between the strength of the weight change and the strength of the existing synapse. It's positive in exponentiated gradients, whereas it's just at 0 for gradient descent, because it's an additive learning algorithm. Okay, so it's better than GD in its respect for physiological and phenomenological evidence, but can it also provide functional advantages? Because we'd like it not just to be a better match, but we'd even like to go a step further and say that it's a better algorithm for training neural networks, period. Now that's going to be hard, as I've said, because gradient descent is the optimal learning algorithm in a Euclidean space. So would there be situations in which it's better to be assuming that you're in a non-Euclidean space in your synapses? Well, one of the interesting things about EG is that it ends up relying on fewer, stronger synapses. So when you look at these synaptic weight distributions here, you can see that there's this longer tail from exponentiated gradients that sticks out the end. And that, we reasoned, might actually make it better for learning in certain circumstances, such as circumstances where you're pruning a lot of the synaptic weights. So we tried training a network on the ModCog tasks, and then removing the weak synapses, and then both observing the performance and retraining on ModCog tasks as well. So first I'll show you what happens before any retraining. Here, this is just a plot of the response accuracy of the network to the ModCog tasks, average across all tasks, for gradient descent and exponentiated gradients, as a function of how many of the synapses we're pruning in the network. And as you can see, as you prune the synapses, a difference emerges between the two algorithms. EG maintains better performance over pruning than GD. And this is in part because the cosine similarity of the pruned and unpruned weights is higher in EG due to the fact that EG is more reliant on strong weights than GD. Furthermore, if you retrain the network, then you find that the EG trained networks are able to much more rapidly get back to a good level of accuracy, even after some fairly significant synaptic pruning, e.g. we've removed 92.5% of the weights in the network. And then we can retrain and get back up to performance relatively quickly, courtesy of the fact that the solution is already very close, as shown by this cosine similarity metric, to what we had after pruning, courtesy of those strong synaptic weights. Same holds even if you prune 97.5% of the synaptic weights. Now, another interesting phenomenon here is that, and this is something that was first observed in the machine learning literature all the way back in the 90s. If you're operating in this non-Euclidean space with these multiplicative learning rates, you can actually have a network that's much more sensitive to relevant inputs that are hidden within a big swarm of irrelevant inputs. So if you do just a basic linear regression, where only a small number of the inputs are relevant to your task. So here, we have n inputs and only 50 of them are actually relevant. As we increase the number of inputs, so what we see is that at first, gradient descent and EG are roughly the same, but in learning this simple regression task, EG is much better when we have a huge number of irrelevant inputs. So here, 2,000 inputs with only 50 of them being relevant to the task. This actually also holds in biophysical simulations. So you can take a biophysical simulation of a neuron and you can train it on this same respond when 50 of the inputs are on, but most of the inputs are irrelevant. So here, this biophysical neuron is trained such that when 50 of the relevant inputs are on, it needs to spike, but when it's under 50, it needs to not spike. So you can see before training and after training what the neuron does. And lo and behold, when you train this network, when you train these neurons, these biophysical simulations of neurons, with GD and EG, EG performs better. And it's because it's better at picking out the small set of relevant inputs from the larger set of irrelevant inputs. And so lastly, and this ties into Matt's talk, we also explored with the help of Olivier training a recurrent neural network to control a simulated arm. So we have these actuators and the arm has to hit various targets. But we modified the task slightly in that in addition to the proprioceptive feedback that the network is receiving about the arm's positions, we added a bunch of noise signals into the system. So this makes it a harder task because now there's all this additional noise that the network must learn to ignore in order to successfully perform the reaches. And what we find is that the networks can learn this. You can see before training and after training, now the networks are able to go from the start to the target. But interestingly, exponentiated gradients is better at this task than gradient descent, both in terms of the speed with which it can learn and the final accuracy that it achieves. Here you're looking at the best seed for both algorithms after 3,000 updates or 6,000 updates, and you can see that the reaches that are produced by exponentiated gradients are ultimately smoother and more accurate than the GD reaches. Okay, so to wrap up, we want an effective learning algorithm. We want an algorithm that can train neural networks to do complicated tasks, and gradient descent is great for that. But we are proposing that exponentiated gradients are a better learning algorithm than gradient descent for computational neuroscientists to use. And the reason is, first of all, it respects Dale's law. Second, it matches the phenomenological data. But then additionally, it's not only matched to gradient descent in terms of its performance in most situations, but it's actually better than gradient descent in situations that are relevant to biology. Notably, if you're considering cases with pruning, if you have to detect sparsely relevant signals, or if you have to deal with a lot of noise. So how should we use these results? I think, as I said at the start, what you're doing with your model depends on what your ultimate goals are in terms of your learning. But if we want to push towards a multi-level model, I would argue that using a learning algorithm, even if it's not fully biologically realistic, that at least is better at matching the biophysical and phenomenological constraints that we have from data, is one step towards a multi-level model that links across these things. And lastly, as a very kind of tangent thought, it's possible that this could be useful for AI, specifically in situations where you're training many interacting parts of which only a subset are relevant at any given moment. Or if you want to be able to prune your networks down for edge computing scenarios where you don't have the luxury of a large neural network. So thanks all for listening. This work was ultimately done by these three folks, Roman, Jonathan, and Arna. And thanks also to Gauthier, Guillaume, Olivier, and Brendan, and Kevin who helped us, and of course our funders. And thanks for listening.
Great. Okay, we have time for maybe one short question, maybe two short questions. Let's start with Alex, and then we'll go to break.
Hey Blake,
Hey.
Really cool work. I have
Thanks.
two very small questions on the distance function that you're using.
Yes.
Like, is it the only? Can you prove that is the only distance function that satisfies this log normal distribution of your weights and like Dale's law? And the second question, can you link it to sort of energy requirements for synaptic updates to even move closer to physiology?
Yeah, so that's a great question. On the first one, I don't know of a proof that this is the only distance function that will produce these properties. It's a distance function that's been well studied in the optimization literature, and that's why we turn to it. But I cannot guarantee that there wouldn't be another algorithm that might also match this. As to the second part of your question, that's actually exactly how we had been thinking of it, that we could view the distance function as basically a constraint introduced by energetic concerns. Like, you don't want to change your synapses too much because it would be energetically costly. But the challenge is that when we've talked to synaptic neuroscientists about this, we get different answers. Some of them are like, yeah, absolutely, that's really cool. And others are like, synaptic updates don't cost you anything metabolically. Don't worry about it. This is a nonsense idea.
Okay,
so I have gone towards avoiding that claim precisely because we've been told by physiologists we shouldn't make it.
Okay, makes sense. Thanks.
Thanks.
Maybe one quick one.
Yeah.
Thank you. Hi, Blake. great talk.
Thanks.
I actually want to know your views about backpropagation,
Okay.
because I think that's one of the constraints, like, oh, does brain really do backpropagation? And is this algorithm is also applicable maybe in other architectures, like local learning rules?
Well, so I think it's worth noting that as I skipped over in the start, there were other biophysical and phenomenological constraints that gradient descent violates, one of which is the locality of the updates, which is what you're getting at. And a lot of people have been studying various local learning algorithms for a while, my lab included. Here's what I am willing to say with a fair bit of confidence. I am pretty much convinced that the brain has ways of estimating gradients. Even if it's not explicitly doing backpropagation, and in fact it's not, as I was arguing here, gradient descent is not an ideal model of learning in the brain. I'm sure that the brain is somehow estimating gradients for credit assignment to some degree. Maybe not perfectly, but it must. And the reason is that you can just see from those equations that if you're not at least correlated with the gradient, you are not learning. You cannot learn effectively without at least being correlated with the gradient in your updates. So any local learning algorithm must on some level be correlated with the gradient to give you effective general learning. And then the task becomes discovering which local learning rules are successfully correlated with the gradient enough to be effective learning algorithms. And that's basically what the game has been in the biologically plausible learning algorithm space for the last decade. And so now we have a variety of algorithms that are correlated with the gradient, that are physiologically plausible, and I think we're arriving at the stage where we need to shift into testing those algorithms more explicitly. But even if we discover various local learning algorithms for estimating the gradients, I still think that we should view those algorithms as operating in this non-Euclidean synaptic space that would lead to these multiplicative weight updates that respect Dale's law and produce log normal weights.
Thank you.
Yeah.
Okay, please join me in thanking Blake once more. Okay, so now we have time for a short break. We're running a little bit late, so we'll try to keep it short. Let's try to be back here at 11:25 to get to the keynote. So, short break.